This is Mr. Matsubara speaking. My presentation title is Proposal for New Hardness Concept Using Herbert Hardness Tester. I am professor of Gunma University. Gunma University is located in Kiryu City, Japan. This is Japan. Here, this is Kiryu. Kiryu City is in about 100 kilometers north of Tokyo. Herbert Hardness testing uses an inverted pendulum type tester. The photographs show the original Herbert Hardness tester. As you can see, the test is on drill edge and milling edge. That would mean the tester could measure the hardness of the edges. This is one of big features the tester has. The original Herbert Hardness tester provided three kinds of hardness data. First, scale hardness, as indicated by the position of the bubble in a curved bubble tube at the end of the first swing. A curved tube with an air bubble and scale. Graduated from 0 to 100 are mounted on top of the original Herbert Hardness instrument. Scale hardness refers to the extent of tester tilting at the end of the first swing. Second, time hardness, based on the time in seconds needed to make 10 single swings of the pendulum on any substance as measured using a stopwatch. Lastly, flow hardness, defined as the scale hardness by time hardness ratio, which is an indicator of resistance to flow. This test method did not become popular due to the time and effort involved compared with other techniques. The Herbert Hardness tester modified bias freely oscillates with damping on a test specimen. The present authors have continued to work towards making improvements in hardness measurement method based on freely damped oscillations. These improvements included the use of rotary potentiometers, radar displacement meters, and image processing. Such techniques allow us to observe freely damped vibrations of the tester on a test specimen. The figure shows an observed freely damped vibration waveform. The envelope line connecting successive amplitude ST is given by this equation, where S0 is the initial amplitude and alpha is a damping factor. As alpha increases, the swing motion diminishes more quickly. Thus, alpha is a newly defined hardness called the damping hardness because it can be considered to represent hardness. I present the following topics. We propose a new hardness measure consisting of the ratio of the natural angular frequency to damping factor and we developed a new Herbert hardness tester incorporating a wireless acceleration sensor. The figure shows an overview of the tester's measurement system. The tester is made of SUS 304 austenitic steel. A cylindrical indenter is made of carbide, 2 mm in diameter and 12 mm in length. The 3 weights are made of brass. 2 side weights are operated by means of leveling screws to adjust the tester's center of gravity to coincide with the center of the cylindrical indenter. Thus, the weights can remain in neutral equilibrium. Vertically above the indenter, a screw-operated top weight. By moving the weight vertically, the center of gravity of the entire tester can be raised or lowered above the center of the cylindrical indenter. For hardness testing, the vertical position of the center of gravity is adjusted so that a single time period of device oscillation is 20 seconds on an artificial sapphire plate. Before conducting a test, the device is tilted horizontally up to 30 degrees. A solenoid switch maintains this initial tilt angle. Then the switch is released by retracting the plunger relative to the main body of the solenoid. The device then starts to freely undergo damped vibration on the test specimen. Two laser displacement meters are set over the Herbert hardness tester to enable electrical measurement of the swing motion. A personal computer stores the voltage change data from the laser displacement meter via a measurement unit. The computer indicates the swing angle as a change in voltage. The figure shows a schematic view of the swing angle measurement principle. The swing angle theta can be expressed by this equation. D is the horizontal distance between the laser displacement meters, and L1 and L2 are the vertical distances between the tester and the laser displacement meters. The angle theta can be precisely measured, and the measurement parameters D, L1 and L2 do not depend on the method of installation. The test specimens used are standard test wax for Brenner hardness from 100 to 600 in steps of 50. One of the authors defined the damping factor as the damping hardness, because the damping factor is considered a physical quantity related to hardness. The damping hardness correlates with brittle hardness number, as is evident from this figure, and is considered to mean resistance to working over working hardness. The relationship is a negative correlation, which means the harder the material, the smaller the value of the damping hardness. A harder material would result in poorer accuracy for the damping hardness as suggested in this figure. The angle theta of free damping vibration is expressed by this equation. Alpha is the damping factor. Omega is the natural angular frequency. Not only alpha but also omega is related to hardness shown in this figure. Although omega should be called the frequency hardness, it decreases with increasing brittle hardness, as shown in the case of alpha. However, the values of alpha and omega differ significantly from the typical brittle hardness values. The ratio omega by alpha is considered a measure of hardness. The figure shows the relationship between omega by alpha and brittle hardness. Omega by alpha increases with increasing brittle hardness and has a stronger tie to brittle hardness than omega. Because the numeric value of omega by alpha is also about the same as the typical hardness value, omega by alpha is apparently a more appropriate hardness indicator than alpha or omega. The authors would like to newly define omega by alpha as the Matsubara hardness, if you agreed. It increases work hardness, indentation hardness, and resistance to flow. As an attempt for further improvement, a wireless acceleration sensor is incorporated in the Herbert hardness tester as shown in this figure. That provides the device with excellent portability. Just bringing the tester and a computer would enable on-site measurement. In conclusion, the present study has demonstrated the following results for popular use of the Herbert hardness tester. We proposed a new measure of hardness defined as the Matsubara hardness, given by the natural angular frequency by damping factor. And we developed a new Herbert hardness tester incorporating a wireless acceleration sensor. Thank you for your kind attention.